Welcome back, everyone. We're going to be talking about networking again. This is part 3. We're going to be talking about layers 2, 3, and 4. Also, don't forget to hit that subscribe button. Today we're going to be talking about layers 2, 3, and 4. We'll also discuss something called ARP Requests and ARP Spoofing, what that is. And then we'll be going over network tools like ping and traceroute, how to troubleshoot different network issues there. And then we'll be covering TCP and UDP and also what the three-way handshake is. And we'll go over Wireshark as well. So just a little background, a little refresher, recap what we covered in the last class. So layer 2 is the data link layer. This is dealing with MAC addresses and switches. So layer 2 is going to use something called the ARP protocol, which we will go over. So ARP is something that happens on the data link layer. This is how other devices discover other devices on a local area network. And then layer 3 is the network layer. This is going to be using things like IP addresses and using routers to route traffic to different networks. And then within the network layer, we'll be going over two different tools called ping and traceroute. And then layer 4 is the transport layer. This is how different connections are established. One of the ways that data is transmitted is with the three-way handshake, and we'll go over that. So let's actually go over Wireshark here. So first of all, with Wireshark, you're going to want to install the program. Okay, so if you take a look at my screen here, we can go ahead and search for Wireshark. You can just go to this website here, wireshark.org. Depending on if you have Windows or Mac or Linux, you can click the download button, go ahead and install the program, and then we'll go from there. So I already have it installed, so I'm actually going to open up the program. So I'll open it up right here. So when you open up the program, you'll notice that there are different network devices down here. And so you can kind of see which ones are using traffic. So Wi-Fi is using a little bit of traffic here, and then other different virtual interfaces there. Also, if you're hardwired in, you might be transmitting data that way. So I've also got a USB-C network adapter for an Ethernet cable for my computer. So if you want to capture traffic, you can actually go ahead and double click on one of these. And there's no traffic on my Wi-Fi. Actually, we're getting a little bit here. So you notice a little bit of traffic's going on here. And we're going to go over what these are. So ARP requests, we'll cover in more depth here. You can also hit the red pause button. So this is kind of a way to see what's going on your network between you and other devices on your network. So with Wireshark, this top part is a list of packets. And then if you want a detailed view of an individual packet, this is what this middle view is. So if I click on this packet, I get more information. We can actually expand that and get additional information there. And then down here is the hexadecimal representation of the packet there. And then up here we've got menu options, so you can change your view, you can see different columns, things like that. So the column number, or the number, is the packet number in order that it was received. The time shows what time the packet was captured. The source shows, where is this packet originating from. The destination is where the packet is going. Protocols, as we talked about, this is how data is transmitted. There are different ways to transmit data. And then the length is just how big the packet is. Destination port and source port, you can actually add these columns here. This is just what port it originated from and what port it's going to. And then you can get additional info here. Okay, so let's actually, I'm going to close Wireshark here. And if I open up Wireshark again, I can actually open up existing files here. So these are called PCAP files. Let me pull one open here. So if I actually do this, and on my desktop, I should be able to just double click on one of these files here. So I'm opening up an existing PCAP file, so you can also do that by going to File, Open, or Open Recent. And so if you want to do your own packet capture, you can hit the blue button and capture on a certain network interface. And you can save this as a .pcap file. And this is just a type of file that gets network packet captures. We'll get into more detail about Wireshark later, but this is a high-level overview about what Wireshark is. It's a way to visualize network information. Okay, so that being said, now that we have a Wireshark installed, let's talk about MAC addresses in Layer 2. So MAC addresses allow computers within a local area network to talk to each other. So data is transmitted to the switches so they can route traffic within the local area network. Remember, different computers on a local area network use MAC addresses to identify each other. But we also need to map those MAC addresses to an IP address so we know exactly where to route the traffic within the network. So if a computer wants to route traffic to a printer, we have to know the MAC address and the IP address in the local area network. So how do computers discover different IP addresses and MAC addresses on the network? So we use something called ARP. So ARP is going to map devices to IP addresses so the devices can find each other on the local area network. So this computer here, it's going to ask who has this IP address, and then it's going to broadcast it to every computer on the local area network, or that subnet. And then if the computer says, oh, that's actually me, then it'll say, here's my IP address based on my MAC address. And then the original computer that asked it can actually store that in something called an ARP cache. So anytime a device connects to a network and wants to see, where's the printer or who has this IP address, it's going to broadcast a bunch of different packets. And computers on the network, if they have that IP address, will reply and say, that's me. And then all these computers are constantly sending out ARP requests so they can build up their ARP cache. Okay, let's go ahead and open up Wireshark here. Okay, so you can see on my screen, this is a packet capture or a PCAP file that I have here. And if we take a look, this is an ARP capture here. So the source, this is a layer 2 protocol, ARP, so we're dealing with MAC addresses. So at first we have this MAC address, which is F092AB, and it's sending out different ARP requests. And it's saying, who has this IP address? Tell me, send the response to this. So this is our IP address. And then the computer that has this IP address says, this is my MAC address, save that into your ARP table. And then after that is cached in the ARP table, we don't have to send an ARP request out to that device again. Now there's something called ARP spoofing. So an attacker can actually respond to an ARP request and pretend to be a recipient. So in this example with the computer, it says, who has .80? Sends it out to everyone on the network, and the legitimate computer will respond and say, hey, I'm .180. But the attacker will also say, no, I'm 1.80. So which one is actually going to get saved? So the one that happens later, or the attacker could actually try to kick this one off the network. There are different ways to do this. But this one's going to override the IP address of the other legitimate one. So let's say you wanted to pretend you were a router. Everyone could route their traffic through your computer, and then you would forward their traffic onto the router. So this is called ARP spoofing. You're pretending to be a host on the local area network, and people trust you. Now, how do we mitigate against ARP spoofing? We can actually prevent ARP spoofing by using static ARP entries. So by sending out the ARP requests, as we talk about, these create dynamic ARP cache tables on our computers. And they last, for a certain amount of time, and then after a certain amount of time, they have to refresh those caches. With a static entry, it will always be the same. The problem with these is it takes a very long time to set up. They're very hard to maintain. Okay, now let's talk about layer 3. This is going to be the network layer. And then we'll also cover some tools like ping and traceroute here. Okay, so ping is a way to test if a machine or a host is up on a network. So if we want to see, okay, is the printer up, or is it even connected to the network, we can use a tool called ping to test the network. It uses something called the ICMP protocol, and this happens on layer 3. Now, in order to use ping, a couple things to keep in mind. The host must be reachable, and the host must be configured to respond to ping requests. So you can actually turn this off on a computer. If you don't want to reply to ping requests, you can turn it off. So if you ping a machine and it says it's not available, that doesn't mean it's actually down. There's a possibility it's just not responding to ping requests. So I'm going to open up a terminal here. You can actually use this on Windows or Mac or Linux. So for this, I'm going to actually be using the ping program. Pretty easy to use. So you can do ping space and then whatever IP address you want to do. I'm going to try to hit Google's DNS server, one of them. And you'll notice we get a reply like this. Now sometimes it'll keep going if it's Linux, so you might have to do Control-C, or on Mac you would also have to do Control-C. So you just hit Control-C, and it would cancel out of that again. Let me try that again. So you do that, and it would just keep going and going with Linux. So I do Control-C, right? And then it cancels out of it. Now what is this output showing us? So I do ping, and it says we're pinging with 56 data bytes, and we get a response right here. So we get a 64-byte response. That's not super important, but it says we get a reply from this IP address, and it's going to try multiple times. The part that is important, though, is it's going to say 5 packets received, 0% packet loss. So this means every time we send a request, we got a reply. So from this information, we can conclude that 8.8.8.8 is up and running. One other thing to point out is that you can type in ping-c and then specify the number of times you want it to run. So if you want to do ping-c 6 and then amazon.com, you would run that, and then it would attempt to run it 6 times instead of just keep going. Okay, so pretty easy tool. What does an what's the output if there's a website that doesn't work? So if I do ping redbull.com, you'll get something like this: request timeout for ICMP sequence, whatever. So this is the attempt number. So I'm going to do Control-C, and it says 5 packets transmitted, 100% packet loss. That doesn't mean redbull.com is down. It may just not be replying to ICMP requests, or ICMP requests might be blocked somewhere along the path from here to redbull.com. Okay, and that kind of brings us to our next topic here. So Traceroute is another tool that we can use, another network tool that can help us map out the path to a target. So if a host is not responding to a request, we could try to use Traceroute to potentially troubleshoot the issue. So Traceroute, it shows us the route to the target, different routers in between. So it lists out the routers and hops, often what they're called, between you and the target. By default, it's going to try 3 times for each hop, and then it can be used to troubleshoot network issues. And we're going to talk about something called TTL, which is time to live, and the importance of that. So I'm going to show you the tool Traceroute, and then we're going to go over the technical specifications for it. Okay, so now we're back at the terminal. I'm going to clear that. Let's go ahead and try Traceroute to 1.1.1.1. This is a Cloudflare IP address here, another DNS server. So you'll see this first hop. This is actually my router, 192.168.1.254. And this is the amount of time it took to get there the first time, second time, and third time. So it took about 1 millisecond to get to my router. And then the next hop is actually going to be my public IP address here. And then it took 3 milliseconds to get there, and it's going to try 3 times. It's good to get an average. And then it goes somewhere else to another router. And then it kind of timed out on that next one. But then on the next one, it gives us the next locations. And eventually by the 10th hop, so it took 10 hops to get from my laptop all the way to 1.1.1.1. So Traceroute shows us what path, this packet took to get there. So if it stops somewhere here, you could say, oh, maybe there's a network issue at the 6th hop. If you don't have access to that, there's nothing much you can do. But if you're in an enterprise network and you're routing traffic through multiple buildings or different routers, you'd say, oh, this hop number 5 this is actually not working out for us. We need to go into the network closet and check out the routing schemes there. All right, so Traceroute just helps us to find the path to where we're going. So how does Traceroute actually work? So the way it works is the client is going to put a TTL flag on it of 1. So the first hop, it's going to get sent to the router. Once it reaches the router is going to subtract 1 from the TTL. So now the TTL is 0. Time to live must have a value in order to continue to the next hop. If the TTL is 0, it's not going to forward it to the next router. So what it does is the router returns the packet and says, hey, TTL of 0, I can't continue. So the client says, okay, I'm going to keep track of this router there. Now, on the next line, it's going to add a TTL value of 2. So it goes from 2 to the first router, and that router subtracts 1 from that TTL value. So 2 minus 1 is now 1, so we can forward it to the next router because it still has a TTL value that's not 0. So then it sends it back, and then on the third try, it does a TTL value of 3. And it keeps doing this until we get to our final destination. So this is a way to get a list of all the routers in between us and our destination. Now let's go into TCP and UDP. I think we've talked about this briefly, but we're going to get into a little bit more detail here. So the session layer, which is layer 4, this is responsible for creating and maintaining connections. So this is how data is being transferred. So if I'm sending a file to another computer or requesting a file from another computer, first we must open a connection. So in this picture here, we got a computer and it's saying, hey, please open a connection. So one type of connection uses something called TCP. So the TCP protocol, it's one of a few ways of transmitting data. So TCP verifies that each and every packet is sent successfully. It starts the connection using something called a three-way handshake. So before you can download your cat picture from Google, your computer has to send something called a sync packet. So SYN, it's going to send an SYN packet to Google. Google will reply with a sync acknowledgement packet. So the purpose of the acknowledgement packet is to say, I got your sync packet, I'm acknowledging it, but I'm also sending my own sync packet. So oftentimes this is called a SYN-ACK packet. And then we must acknowledge Google's SYN-ACK packet. So this is called the three-way handshake. After the three-way handshake has opened the connection, we can start transmitting and downloading data. So our computer says, please open a connection. Google says, okay, I acknowledge the request. And then we say, I'm acknowledging you got my request. Now once the data transfer has completed, once we download that cat picture or whatever resource, we close the connection. So we send something called a fin packet, short for finish, and then Google will actually send us an acknowledgement and its own fin packet, and then we acknowledge Google's fin packet. So TCP has a lot of downsides. It's good for several things, but it's also not good for other things. So TCP is really great for reliability. And so when you want to make sure every part of a file is downloaded or resources intact bit for bit, we use TCP. So TCP is good for file transfers, viewing web pages, online shopping. We need to make sure everything is correct bit for bit. TCP is not great for speed though. So we're going to talk about something called UDP. This is how data is transferred for things like live streaming and broadcasting, things where we don't necessarily need every single bit. UDP connections are used when speed is prioritized over reliability. With UDP connections, it's okay if we lose a few packets here and there. So UDP is a connectionless protocol. There's no three-way handshake. So one example is our computer requests a live stream from Twitch. So Twitch is a popular gaming streaming website, so you can watch other people stream content. And so Twitch is using UDP because it's a live stream, and this is where speed is more important than reliability. And so Twitch says, I'm going to send you data If you get it, great. If not, it doesn't matter to me. What's important is that I send data as fast as I can send it so you can get the latest and greatest. Because imagine if you're 5 minutes behind on the video, it's not going to be as useful. So with live broadcasts, live video streaming, UDP is generally going to be what's used. Okay, let's talk briefly about port scanning here. We're going to cover port scanning in a lot of depth in the pen testing section, but for now let's just go over it a little bit. So with port scanning, every computer has 65,535 ports on it for TCP and UDP, so you could double that number if you wanted to. That would give you the total number of actual ports. So when we do a port scan on a computer, we want to see if a port is open or closed on the machine. The reason is, when we're doing pen testing, we can only interact with open ports. If a port is closed, we can't interact with it. If a port is filtered, we need to do a little bit more reconnaissance to see what's going on. Okay, so we're also going to cover something called Nmap later. This is a great networking or network scanning tool. But this is what's going on. So if we want to do a network scan and see if a port is open, in the first example here, so we've got a computer. It's going to send a SYN packet. We get a SYN ACK. We set a reset packet to actually close that connection. So with a port scanner, it's going to send the SYN. We get a SYN ACK. We send a reset. There are 3 packets total, so we know this port is open. In the next example, if we send a SYN packet to try to open up or connect to a port on a computer, and the computer responds with a reset acknowledgement packet, we know this port is closed. So the reset packet tries to reset the connection and say, I'm not open for business right now. So with 2 packets, we can know this is a closed port. And then a filtered port, usually this means it's behind a firewall or traffic's being filtered somehow. We send 1 packet, we get 0 packets as a response. So a lot of the times we might need to do a little bit more reconnaissance just to make sure, that packet or that port is actually closed or if it's actually open there. Okay, so what did we cover here today? We talked about layers 2, 3, and 4, different tools like ping, traceroute, talked about ARP and ARP spoofing. We went over TCP, UDP, and the 3-way handshake, and we also used Wireshark. One thing is that a lot of these things are great interview questions, so the things that we covered today will be asked a lot in different interviews, and we might cover this later in some of our interview classes here, a lot of tech questions. So I hope you enjoyed this networking section. We're going to dive a little bit deeper into the network questions and topics here in the next couple of classes. Hope you enjoyed, so stay tuned and see you in the next class.